All right, so I was saying we're going to begin a new topic, that is equilibrium of particles. And under this topic, okay, let me just say this topic is one of the simplest topics that you're going to have in statics. Yeah, so let us quickly get into business. All right, so in case you want my line or anything, you can use these lines on the screen. If you have questions in engineering and other courses, you can simply just ask me using the lines on the screen. All right, so under this chapter, we're going to discuss, or we're going to be introduced to the concept of free body diagrams of any particle. And if you remember the time I was just introducing statics, I remember telling you that one of the most important things in calculus, I don't know I'm mentioning calculus, in statics, is drawing free body diagram. It's not only in statics, but also in any science. Free body diagrams are very important. They help out to solve a number of questions. In other ways, they help out to make the solving simple. Yeah, so I'm going to show you how to draw the free body diagrams, because there are some lectures which very strict to a point that if there is no free body diagram when solving a question, they'll consider that you are just copying from someone and they'll not give you full marks. And then apart from that, I'm also going to show you how to solve particle equilibrium problems using the equations of equilibrium. So I'm pretty sure you guys know the equations of equilibrium. If you don't know them, you're going to see them as we proceed. All right, so the conditions of equilibrium of a particle, so they are just based on Newton's first law of motion. We all know that Newton's first law of motion states that a particle remains in its state of rest or constant motion as long as there is no external force that is applied to it. So if you leave a cup on a table, that is then an example. If you leave a cup on a table, you go somewhere, you stay there for 50 years, as long as there's no external force acting on that cup, you still find it in that same position you left it. That's Newton's first law of motion. And then we know to say Newton's second law of motion is simply just based on this formula, which is the force. The force of any given object is directly proportional to what? To its acceleration, or the force acting on a certain body is directly proportional to its acceleration. Yeah, and the constant of proportionality is called what? The mass. So a lot of people know it as force is equal to mass times acceleration. So this is just a constant of proportionality. And then we have, okay, let me just state it in this way. The force acting on any body, you have a body, then the force acting on this body is directly proportional to the mass of this body and the acceleration of this same body. Let me say it that way, maybe. Let me not add in a lot of words. All right, so that is basically what defines the conditions of equilibrium of a particle. Okay, so let's quickly move on. So the applications, so the equilibrium of particles are usually, okay, here I think I only managed to, okay, not really managing, but I only put two applications, but there are a lot of applications, or there are a lot of, you can apply this equilibrium of particles in solving a lot of problems. So this is just one of the problems that we normally use this is the problem that is normally solved using the equilibrium of particles and its equations. Yeah, so when you're dealing with springs, we know to say the force in a spring, we know that to say F in a spring is given by Ks. Yeah, so some books, they put negative in front. Yeah, depending with the direction you are considering there. So it's force is equal to Ks, which is, I mean, and this force there is the one that you are seeing here. Okay, so this is the equation I was writing there. And then the other one is when you're dealing with cables and pulleys. So when you're dealing with cables and pulleys, we also, I mean, when you're dealing with these, as long as they are in static equilibrium or they are just in equilibrium, in short, you can use those same equations. The summation of forces is equal to what? MA. But since it's in static equilibrium, remember we're learning about statics, meaning when something is static, it's not moving. Its acceleration is what? Is equal to, I mean, when something is moving with a constant speed, remember, according to Newton's first law of motion, it says that if something is at rest or it's moving in constant, I mean, with a constant speed, it will continue moving with the same speed as long as there is no external force that has been added to this a mass here or this object. Yeah, so what that means is that if you have, we know to say the formula for acceleration is V final minus V initial over T. This is the formula for acceleration. Now imagine that the V final, the V initial here, V initial and V final are the same. And let's take, for instance, if it's 2 meters per second, even this one is 2 meters per second. You have 2 minus 2, you're going to get on top there, the numerator will give you what? Will give you a 0. Then maybe it has taken maybe 5 seconds. Yeah, so you say 0 over 5, the answer will be 0. So as long as this particle is in constant motion or it's static, yeah, it means that the acceleration is what? Is 0. So if the acceleration is 0, it means that the summation of forces is going to be equal to what? 0. This is the reason why whenever we're dealing with the equilibrium of particles, the summation of forces should always be equated to 0, which implies that all the forces in the x plus all the forces in the y, they add up to what? 0. Or simply, you can, or you can simply just say summation of forces in the x. Yeah, so let me write it. Summation of forces in the x is equal to 0, and summation of forces in the y is equal to 0. So as long as you're dealing with equilibrium of particles, these two formulas are very vital. Okay. Let us see how we can draw a free body diagram. So if you have a question that is like this, and then your focus is somewhere there, how can you draw a free body diagram here? So there's some engineers that will tell you to say, you need to have engineering feelings. You need to know to say, okay, where is this force facing? If we say this cable here is in tension, let me draw one cable here. If we say this cable is in tension, what is the direction of forces in this cable? Or let me write it like this. We have a pole here. Then we say we have tied two cables here, or there's a pulley here. Let me say there's a pulley here. Then there's this cable which has gone this side. There's also another cable which has gone this side. Then they tell you to say these two cables A and B are in what? They're in tension. If they're in tension, the question is, what is the direction of the forces in this cable? So now you need to use your engineering feelings to know, to describe, or to feel where the force, I mean the direction of these forces is going to be. Yeah, so how do you know? How do you use those feelings now? So you need to have those feelings. So you need to start developing such feelings. They are called engineering feelings. So the direction of these forces will be like that. Yeah, so you need to know those things. So if we consider this part here, and they ask you to say, draw a free body diagram just for this part here. One thing you need to know is that we have a joint there. So this joint is what will cause one force to face what? To face up, the other force will face what? Down. And then this force which is facing down, we'll take it as the weight because we have something that has been tied here. So we'll take it as the weight of this object down. And weight is given by mass times what? Gravity. We're using G here because it's suspended in the air. Yeah, so this is exactly what we're going to do. And then the force that is facing up there is the tension in the rope there. So that is how you are supposed to do. So the free body diagram for this will be like that. So that is the free body diagram. And then we move on to the other example. You may also be given such an example there. Then if your focus is here, means that if, let's say, for instance, your focus is there, and then they ask you to say, describe, or rather draw the free body diagram to show just this joint here. So one thing you have to understand is that there is something like a joint here again. Let me say there. So we're going to have one force which is going to face up because we know that this cable here is in tension. So whenever you are dealing with a joint which consists of members that are in tension, for members that are in tension, their direction or the forces, they are all always away from the joint. Yeah, they are mostly away. Not let me not even say mostly, as long as it's in tension, it's not in compression. So if they, let me give you something like this. If let's say you have a truss, you have something like this. What example can I give? Okay. Sometimes you might be, okay, I'll explain this better when we start discussing trusses, because when I introduce them now, you might just end up getting confused. All right, so what you should just put in mind is that anything, if you have a member that is in tension at a joint, its direction of, or its sense of direction is always away from the joint. If it's in compression, the sense of direction is going to be towards the joint. But in this case, it's in tension. This cable, when you look at this cable, it's in tension. So we expect the direction of of the force to be up like that. So this is how you come up with free body diagrams. And then we have a joint there. These two cables are also in what? In tension. So their directions again will move away from what? From the joint. They'll point away from the joint. Okay. So that is the free body diagram there. Okay, so.
Sir, I have a question.
Okay. What's the question? Hello, not getting you. What's the question?
Hello.
Yes, I'm not getting you.
Okay. I've gotten the concept of tension and yeah, the weight. But my analysis is that the weight is the only, can say, object causing having a force. But why do we consider the tension upwards?
Oh, on which question? Oh,
first diagram.
On this one here.
Yes.
Oh, there's a person who asked that question in class, and the lecturer responded and said, you need to have engineering feelings. But okay, let me try to explain it in my words. So your question is, we have the weight pointing down. Why is it that we're having the tension pointing up? Is that the question you asked?
Yeah.
Okay. So I'll give you this example. Imagine that you have a cable here. Okay, let me just draw it here. Let me just use the same example. Imagine that we cut this cable here. If it's in tension, like we have something that is pulling this side, it's pulling it going this side, then there's also some other thing which is pulling it going this other side. So now as we continue pulling the cable, and then it automatically just disconnects here, where do you think this side will go? And where do you think this other side will go?
The down part will be down and then up, upward.
Yeah, this one will go with force going up, isn't it? Yeah, it will go up,
Yes.
with a lot of force, which implies that the force that has pulled this to go up is the same tension that was in the cable, which tells us to say the force here was pointing up. If it was pointing down, this cable would have gone down instead of going up. Maybe that's the simplest way I can explain that.
Okay, yeah.
All right, so let's quickly proceed. So when we talk about coplanar, coplanar forces, I think I explained this the time we were looking at vectors. So coplanar forces are simply just forces on the same plane. Yeah. So if you have forces on the same plane, how do you draw the free body diagram and how do you solve them? So the free body diagram, okay, this one, let me just say, it's already a free body diagram on its own. So the other thing that I can just explain here is that when you've been asked to find anything, in short, you just need to apply the same equilibrium equations that we discussed, which are the summation of forces in the x is equal to 0, and all the summation, all the forces in the y equal to 0. So these are the two important equations that you need to apply on such a question which comes in this way. Yeah, so questions may even be more complicated than this. Yeah, but what you just need to be putting in mind as you solve such a question are the directions of the arrows. So you know to say, to find the resultant, if F1 is a resultant, it means that its X component will be what? Will face this side, and the Y component will face on the positive Y. For this one, the X component will face where? It will face on the positive X, and then the Y component will face where? Negative. For you to move from this point to that point, you need first to go down like that, then you go like that. Even if you take the top route there, you still move in the same way. You move like this, you first go like that, and then go down. So
what's the definition of coplanar force system again?
Yeah, the coplanar force system, these are just forces that are on the same plane, in short. We have the XY plane here, and then we have different forces, on the same plane. I think that's the simplest definition. It can even be in 3D. Yeah, it can also be in 3D, where you even have the Z-axis. But as long as you have 2, 3, or 4 more forces that are on the same plane, they are called coplanar forces. Okay, so this is what I was just talking about. Yeah, so let's look at some examples. How can we apply these same concepts, the equilibrium forces and other things? Yeah, so this is a question here, and it says determine the tension in the cables BA and BC necessary to support the 60 kg cylinder in the figure. Okay, so like I said, the most important thing here is, the most important thing here is just knowing the direction of forces. So if you look at if you look at the cables here, and we take this joint here, the force in this cable, or the tension in the cable this side, as long as it's in tension, we consider this to be moving away from what? From the joint. Even here, we consider it to be moving away from the joint. Even this one here, we consider it to be moving away from the joint because we know that all these three cables are what? Are in tension. Yeah, so.
Sir,
Okay.
I have a question.
All right, you can ask.
What of a case where you are not told if it's in tension or compression?
No, this here, whether they tell you or not, but just practically or just by looking at it, you can see that this when this is suspended in the air, it's like it's pulling all these cables down, and as it is pulling the cables down, you can see that this cable is connected here. This one also is connected here. So when you pull this down, or when this is pulling the cables down due to gravity, the force here quite right to face down. The force in the what have I done? Sorry for that. Okay, the force in this cable here, quite right to know that it's forcing, it's facing down there. But how do you know that this is facing away? I mean, this one is, yeah, it's facing away from what is the joint. It's not it's not going towards the joint. How do you know that? It's because as you pull this down, I think this is where I think I now understand why he said you should have engineering feelings. As you pull this down, I think you can just feel that, okay, here, there's some tension that is in the cable, because for this, if this is in compression, you expect this, if this is in compression, if this cable, for instance, is in compression, you expect this cable to bend either like that or like that, or you expect this cable to bend like that or like that. If at all this this thing is going up, if you're trying to take it up, yeah. But the fact that you are pulling this block down, this cylinder down, that is what is going to tell us that the forces in this in the cables are what are like, I mean, let me say the cables are like trying to stretch, and anything that is stretching is mostly in what? In tension. Yeah, it's like you're trying to stretch the cables. I think that's the simplest way I can explain it otherwise.
So what's the risk of exchanging the two, compression and tension?
The what?
As in risk of exchanging the two,
The risk.
replacing rather, yeah.
The what is the direction of forces. When you just miss out the direction of forces, you obviously get the wrong answer. Because if you get this to be pointing this side, means that the time you'll be considering the y components, this one will get a negative sign, and then this one, when you say this one is facing this side, and then you take this one maybe facing this side, when taking the x component of this one, instead of taking the positive x facing this side, you're going to take negative x facing this side. So the signs will be different, and as a result, you get the wrong answer. Okay, so if you have such a question, then you draw your free body diagram. So this is the free body diagram here. What you're seeing here, the free body diagram. Yeah, so this part here is what I'm saying, it's a free body diagram. And we've been given the mass of the cylinder. So to find its weight, we know to say weight is equal to what? mg. So the mass is 60. You're multiplying it with what? The gravity, which is 9.81. When you multiply that, you get the weight. So let me just do the calculations. We have 60 multiplied by 9.18. So that is 550. So the weight is 500 and what? 50.8. We write it here. Weight is equal to, so we have 550.8. newtons. So that is the weight we have there. So now we can solve the question because it's straightforward. Let's do it together. So we said we take the summation of forces in the x and in the y. So we're going to be looking at the free body diagram when solving this. So we say summation of forces in the x should add up to what? 0, because this particle or this cylinder is what? In equilibrium. So let's start with the forces that we start with the forces in the x from the cable AB. So from the cable AB, I want a color that I'm going to be seeing both. Okay, let me try to use okay, let me use red. Okay, so what we're going to start with the forces that are in this cable. So in this cable, we have, I'm going to draw something like a triangle there. I think it's already drawn here. So let me just use the free body diagram here, which is already drawn. So the forces in this cable there, the x, the x component of this force, since we've been given this small triangle there, it means that it's just the same as us being given the angle. But given this one, at least it's a bit easier for us to find the solutions even without a calculator, because they're just going to say this tension A. Don't like using red nowadays. Okay, so the tension TA is going to multiply itself with what? You look at the number that is in the x. So the number that is in the x here, if you look, we have 4. So the x number there that we have is 4. So we're going to say 4 divided by the hypotenuse there, which is 5. Because this one is adjacent, we know to say when you're dealing with cos is, we're dealing with the x component of a triangle that is like this. The adjacent, we're dealing with the adjacent, for instance, the angle is there. If this is the adjacent, you say if this is the adjacent and you're trying to find this, you simply just say the hypotenuse there, you multiply it with what? It's like this. We know that cos theta is equal to the adjacent over the hypotenuse. So it means that you're just going to multiply cos theta times the hypotenuse. So the hypotenuse that we have there is what? The tension in A. And then we're trying to find the adjacent. Yeah, so the adjacent is what we're trying to find. So the adjacent here is this one here. But we have not been given the angle, we've just been given the number. So we just pick the number that is in the x there divided by 5. So in the x we have what? We have 4. So in the x we have 4. Let me just erase this. Okay. So in the x we have 4 and then divided by 5. And then it's facing towards the negative x-axis if you check here. So we put a negative in front there. And then when you look at the other part, which is the tension C, its x component is facing this side. So we are also using cos because, we are using cos because it's because this side is adjacent to what? To the angle that we have been given there. So we're going to have something like this. It's facing towards the positive, so we write a positive there. And then we say TC cos 45. Then we say, do we have another force that is in the x? No, we don't. So we equate this to 0. So from there, we can simply just say this can cross the equal sign, can go that side, so that you have TC being equal to, so if you want, you can say 5. Okay, let me do this. Yeah, so TC is going to be equal to when this crosses the equal sign, you have something like TA, open brackets 4/5, then everything over what? Cos 45. So this is our first equation that we can keep. And then we move on to the y component. So we say the summation of forces in the y should also add up to 0. So in the y, we add all the forces that are in the y. So in the y, we have the y component of the cable AB. The y component of the cable AB is facing up. It's facing up when you check there, meaning you're going to have, yeah, so it's facing up. Let me be using yellow. Maybe yellow will balance on both instead of me changing colors. So the y still worse. Okay, so the y component of TA is facing up. So since it's facing up, it means that it's facing towards the positive y. So we can say TA, and it's opposite to, okay, let me not say it's opposite. We've been given a small triangle there, and the side there, which is coinciding with the same direction of the y component of TA is 3. I mean, we have a number there which is simply just 3. So we're going to put 3 there, and then over the hypotenuse, which is 5. And then the y component of TC is also facing up. So this is going to be positive TC. And since it's opposite to the angle there, so we use sine 45. Because from SOHCAHTOA, sine is the one that deals with the opposite and the hypotenuse. And then we also have another tension in the y, which is the tension what? We have the tension TB. The tension TB here. So one that we found to be 550.8. So this tension here is in the y, but it's facing down. So we say minus, it's facing towards the negative y. So we say negative 550.8, and then we're saying everything should equal to 0. So here it's just a matter of solving the two simultaneous equations. This one and that one. So in the second equation where there is TC, I'm going to replace with that. So I have TA 3/5 plus TC is simply just TA 4/5 over cos 45. And this is going to be what? Equal to, when we take this to the other side of the equal sign, this will be 550.8. Okay, so after doing this, here it's just a matter, I think, of using calculators and making T as a subject of the formula. So let me quickly just do that in the remaining 5 minutes, so that in the next session we just do those two other examples. So when you factorize TA there, you're going to remain with what? 3/5 plus 4/5 cos 45. So cos 45, if you don't want to use a calculator, you can say √2/2, which tells us to say we can also write it as, I can just put 8 on top there. So it will be 8/5 √2. And there's supposed to be sine theta this side. I forgot sine 45. Sine 45 is also what? √2/2. So I think if we put sine 45 here, this and that will cancel. So we'll just remain with this. We'll just remain with 4/5 there. Then we say this is equal to 550.8. So when you add the two, you get 7/5. Then this is equal to 550.8. So when you cross multiply and divide by 7, the value of TA becomes what? So 550.8 times 5, then divided by 7. So we're getting 393.4 newtons. That's the value of TA. Then we find TC. So TC, we simply just replace. I've even forgotten how the expression for TC was, but I think it was something like this. 4/5 over cos 45, which is the root of 2/2. So our TC is going to be equal to, what is TA? We put 393. We divide that by cos 45, then multiply it by 4, divide it by 5. So it's giving us 445.1 newtons. So these are the two values of TA and TC that we have found. So it's very simple. I don't know where the mistake was. Let's see. So TA, to them they found 420. Should we resolve this question again? Okay, let me just try to do it quickly. So the first one that we had was TA. So TA, we're going to have so all the summation of forces in the X is equal to 0. So in the X, we're going to have 4/5 TA, and then for this other one, we're going to get so this one is negative, then this one is going to be TC, positive TC cos 45, and then we say this is equal to 0. Then in the Y, we're going to have, so the summation of forces in the Y is going to be equal to, so we have 60 times 9.81. Oh, no, the solution was just okay, but the problem was here, supposed to be 588, this one. We wrote 550, 588.6. Yeah, not 550. So this was the only problem that we had. I wanted to get surprised at this question. Yeah, so that was the only issue. Yeah, that's what that was the only problem that we had here. It was just finding the weight there. So it was supposed to be 588. All right, so we join using the same link so that we proceed. We finish up these two other questions.